Welcome to the demo on optimizers in deep learning. In this demo, we will learn about the effects of various types of optimization routines that deep learning practitioners typically use. And these include gradient descent and its variants such as Newton's method, momentum, and Adam. This assumes that everybody's familiar with the lecture material on optimization for deep learning. This is going to be a stylized demo, and we're not actually going to do deep learning in this example because it's a bit hard to visualize how optimization actually functions while updating models with very large number of parameters. So this will be a fairly simple demo with only 2 parameters as inputs, and we're going to optimize functions over 2 variables. Okay, so here's some boilerplate code to get started, and this basically implements simple functions such as function generation, its gradient, and various types of optimizers. We will look into each of these methods as we go along. Okay. But first, let's start with vanilla gradient descent and see how that works. Okay. So as a simple example, let's see how gradient descent works while optimizing perhaps the simplest possible function over 2 variables, which is just a parabola. Okay, so let's try to optimize functions of the form f of xy. It's a function of 2 variables, and it's going to be just a parabolic function. Okay, so let's see how this function looks like, and this is just a parabola in 2 variables. So the routines that we have implemented here is it's easy to generate these kinds of functions. So I'll define basically a parabolic function, which is basically a quadratic with coefficients 1 and 1. So x squared plus y squared. There are other coefficients for x, y, and x and y as well, which is just set to 0. Okay, so this is just a parabolic function, and we'll see how to optimize this function. So everything is implemented in Torch in this example. So we need to start. Our gradient descent somewhere. So I'm just going to optimize it to some arbitrary number. Let's say 3. So the point 3 and 3. So x equal to 3, y equal to 3. Okay. It should be easy to see that this function has a unique minimizer at the origin 0, 0. Okay, but we're going to implement gradient descent and see its trajectories starting at 3, 3. Okay, so let's declare the optimization routine. This is just regular gradient descent, and the function that we've implemented here is, it can simulate both gradient descent and also variations such as momentum and Adam. So if you include the first order gradient aggregation, that's momentum, and the second order gradient aggregation, that's Adam. So I'm going to set both the first and second order terms to 0, and only look at the learning rate. So the learning rate in this case, let's just choose it to be something like 0.5. Right. So this is vanilla gradient descent starting at 3, 3. So I'm going to see how this procedure can be visualized. So I will plot the entire trajectory of gradient descent starting with this initialization point. Okay, so it's the parabola function ran with number of steps. So the function show path will display both the function that we're trying to optimize as well as the path generated by the optimizer. Okay, so that's what we're going to do. Gradient descent. So let's plot it in red. Okay. So let's see how this looks like. So right now we're just going to plot the function, and we're going to see that we start at the point 3, 3. And if we run, like say, maybe a couple of steps of gradient descent, we will see that we start descending down the valley. Okay, so how we visualize this plot? Well, each color is basically like a contour of equal height. And as we go away from the origin, the height increases, right? So it's a parabolic valley. And if we descend down this valley, we go towards the origin. Okay, so this is quite clear. And if we run it for several number of steps, we will converge will converge closer and closer to the origin. So this should be fairly intuitive. You can play around with various learning rates, various number of steps. So for example, if we decrease the learning rate, then progress will be a bit smaller per step. On the other hand, if we increase the learning rate, progress will be quicker. We quickly converge to the origin. We can also change the initialization point. And it should be very clear that because of the symmetry around the origin, it shouldn't really matter where you initialize, right? So it doesn't really matter. So this is a very simple function, and there's nothing funny going on here. Gradient descent is actually perfect. Let's now look at a slightly more interesting example. So let's now try to optimize a more complex function, such as a hyperbola. The hyperbola in two variables looks like something like this. Okay, so this is basically well, it's not exactly hyperbola. It's hyperbola in y, but a parabola in x, right? So the interesting thing about this function is that it is now non-convex. So what does that mean? So if you try to visualize, so I'm going to change the function to say x square minus y square. Let's keep the initialization, let's say at 3. Start with let's keep the same optimizer. So we'll just run gradient descent again, but we'll try to visualize how this works. So if I run gradient descent on the hyperbolic function, one can see that the level sets or the contours of this surface are quite different. So first of all, it's non-convex in the sense that it's there's a valley. There's a valley in the both in the x in the x direction, but sort of an inverted valley in the y direction, right? Which means that this is an example of a function where the origin is no longer a minimum, but instead a saddle point. Okay, so so the origin in this case is a saddle point. Unfortunately, all too common, we encounter loss functions in deep learning which have tons of saddle points. So this is not a pathological example in any sense. Okay, so let's see what happens if we run gradient descent on this function. So if you start at a point on the x-axis, that's minus 3, 0. If you run maybe a couple of steps of gradient descent, we'll see that it tends to get attracted towards the saddle point. Okay, notice that it's not a minimizer, right? So the minimizer is actually at plus or minus infinity along the y-axis, right? So it's not a minimizer. So so if you initialize at any point in the x-axis, then you start moving towards the saddle point. However, if you veer away even a little bit away from the x-axis, let's say that I start at point say minus 3, plus 0.5, you tend to sort of not be attracted to the saddle point. It's easier to visualize this if you imagine sort of rolling a ball down the saddle, right? So if you roll a ball down the saddle, it'll go towards the center of the saddle and then eventually veer off to the sides, and that's really what's happening here. And very quickly, the iterates of gradient descent basically diverge off to plus or minus infinity on the y-axis. Okay, so this is an example of a function which is non-convex, and in non-convex functions such as these, it's actually super important to choose an initialization, right? So it's super important to initialize carefully. So I mean, just maybe play around with a couple of other initializations. So again, on the x-axis, it doesn't really matter. If very carefully on the x-axis, if you initialize it, doesn't really matter. But even if slightly above or below the x-axis, you tend to see divergent behavior. So just off the x-axis, and start diverging, right? So you can play around with learning rates and so on here, but really the initialization is key in non-convex optimization. Okay, so that's the gradient descent is actually very susceptible to initialization for general functions. A somewhat more insidious issue here, right? So let's stick to convex functions. Okay, so even in the case where the function that you want to optimize is convex, even there, a gradient descent can be quite susceptible to various choices of parameters. So as an example, let's try to optimize a function that's ellipsoidal. Okay, so it's a function which looks like something like this, right? So it's so this is an example of a function which is I mean, if you write down the general form of a quadratic, you can see that this looks ellipsoidal. I mean, the contours of the level sets are ellipses in the 2D plane. Let's see how gradient descent works in this example, right? So I'm going to implement gradient descent to optimize f of x, y. Okay, so I'm going to just copy a bunch of code, right? So this is the function. So I normalized to square root by square root 2 just to make the figures nicer, and I initialize in a particular way, right? And let's start optimizing this function, using gradient descent. Okay, so without any steps, just the initial point, you can see that the level sets are now ellipses, right? So, and these are skewed ellipses. So this is skewed in a particular angle, as well as stretched along the major and minor axes. So what happens if we run gradient descent here? So let's run a couple of steps of gradient descent. So we would expect that this function, the iterates of gradient descent move towards the center of the valley, which is centered at minus 7.5 minus 0.5. So the trajectory should move from the red dot here towards the center of the black ellipse. But if we observe the contours, that's really not the direction of steepest descent, right? So the gradient is maximized, or the rate of descent is maximized almost perpendicular to that direction, right? So if we run a couple of steps of gradient descent, we'll see that they're not really moving towards the center of the black ellipse, but rather, towards the direction of the gradient, right? And the gradient is maximized sort of perpendicular to these levels, the surfaces of the level sets, right? So there's a fundamental problem with gradient descent, is that it is inherently greedy. And because it's inherently greedy, it just follows the path of most gradient, which is not necessarily the path that achieves the final answer the quickest, right? So gradient descent tends to have an oscillatory behavior like this. And we can see this in deep learning as well, right? So if you just follow the locally steepest direction, oscillations tend to happen quite a lot. And so this is a problem. So how do you fix this problem? And one way to fix this problem is to just simply reduce the learning rate, right? So if you don't take aggressive steps, and the reason why we oscillate is because we have overshot our goal here, right? And we have to come back and forth, back and forth. So if we take smaller steps, then presumably we don't oscillate that much. But the price you pay there is that now progress towards the optimum is much slower, right? Because you're choosing very small steps, and the step size is small, therefore it take a long time to converge. Okay, so we want we want fairly fast convergence, but we don't want oscillatory behavior. One way to achieve this is via a technique known as Newton's method. So let's try to implement Newton's method. I won't explain what Newton's method is, but suffice to say that Newton's method basically takes a function and then scales its gradient intelligently, right? So if you recall how gradient descent functions, you compute the gradient and use the gradient to update the weights, right? But the gradient is a vector, so you can choose to upweight and downweight certain directions of that vector. And Newton's method does this in an intelligent manner. In particular, it does this by preconditioning the gradient using what's called the Hessian, or the second derivative. Okay, so we won't get into the details of Newton's method here, but suffice to say that it sort of makes this loss surface sort of nicer looking and more circular in nature as opposed to elliptical. So it unskews the ellipse, as it were, in some sense, right? Actually choose the same learning rate. Let's choose the same learning rate. which is like a simple learning rate, let's say 0.5. So what will happen here? But so now since we have sort of unskewed the ellipse, the elliptical contours, it is similar to the original parabola example if we run Newton's method, right? So it becomes as simple as running a parabola. So let's just run a couple of steps here. So if I plot both the paths, path 2. So the path 1 again is the original gradient descent. Path 2 is the Newton's method. Newton's method achieved by scaling the gradient to the Hessian in each step. What do we get? So we should 2 steps. I should not do much for gradient descent for some reason. I'm plotting the same thing. Sorry. So what happens if do this? So gradient descent tends to follow its own path, but Newton's method actually directly goes towards the optimum. Right? So in some sense, we're pretending we are unskewing the ellipse and making it similar to the parabolic optimization, the first case. Okay, so this actually is one approach to fixing the issue with gradient descent, is to precondition the gradient with the Hessian. So this is a learning issue here. It's probably too big. Yeah. So if we like a bit more modest, and this is what we get. Okay. So Newton's method is one approach of enabling the pathologies of gradient descent to disappear. But the issue in Newton's method is it's actually multiple issues. One issue is that it is just difficult to implement in deep learning. Right? You need to compute the second derivative, which is basically the Hessian. Now the Hessian is not just a vector, but actually a matrix. So it's d square f by dx dy. Right? So for every if you have input of d variables, your Hessian is d square dimensional, which is just impossible to do in deep learning because the number of variables is very, very large in general. Another somewhat curious issue in Newton's method is that if we try to say, for example, optimize the hyperbola using Newton's method, right, let's see how that works. So if I try to just do Newton's method for this particular case, right, and we'll just keep the learning rate the same. Right, let's see a couple of steps, and I'm going to plot both regular gradient descent, which you've already seen, right? It has this saddle point issue, and the and Newton's method on this function, on the hyperbola function. Okay, so what should that give us? So we know already that gradient descent will diverge to infinity if we initialize off the x-axis. But what does Newton's method do? Oops. Oh, I'm sorry. I need to, since everything's in torch, I need to make sure that the variables are not integers but doubles. So I'll make the double value. Okay, so they look kind of the same. Let's increase the number of steps. So if I increase the number of steps to say, okay, make the initialization a bit more distinct. Right, so if I make the initialization a bit more distinct, so notice now that it's actually curious that the trajectory of gradient descent diverges as we know before, but Newton's method gets attracted to the saddle point. It's kind of curious, right? So that's as one feature of Newton's method, that it seems to be attracted to saddle points, which may or may not be desirable. Right? Saddle points are not desirable because they don't represent true minima, either in the local or the global sense. Right, that's something to be worried, careful about. And second, also, it's just difficult to implement in deep learning. Good. So what's the alternative? So one alternative is what's called momentum. Okay, so momentum has the impact of simulating the effects of Newton's method. So it is not exactly a second order method. It still only takes in first order information such as gradients, but using this memory trick, as we discussed in class, it simulates the the effect of Newton's method and stabilizes the trajectory. So how exactly does that happen? So let's again take the ellipse example. Right, so let's see how momentum works in the ellipse example. So if we go back to the ellipse, I'll this is exactly same function as before. Let's start again at 0 number of steps. I'm going to replace the Newton's method with moment. So in code, the way we do this is that we add first order information, right? So it aggregates the the gradients that occurred in previous time steps according to this history parameter 0.9. Okay. So this is momentum. So let's look at how that works. So if you have 0 steps, then we initialize this at the same point. So both gradient descent and momentum descent are initialized at the same point. But let's take a couple of steps. See how they work. So actually, let me make the learning rate a bit more aggressive to visualize the differences. So as you can see, there's an aggressive gradient learning rate. The gradient descent is tending to oscillate a bit. But if you run it a few more iterations, as you can see, the trajectory of momentum is much smoother, right? It's a much smoother form of gradient descent, right? So that is the reason why we tend to use analogies of balls rolling down the hill and making the ball heavier in momentum, right? So in some sense, if you have a lighter ball rolling down the hill, it will tend to jump around quite a bit. But if you add momentum, then that has the effect of damping the trajectory, right? So the oscillations are considerably damped in momentum compared to standard gradient descent. So you have much smoother trajectories in momentum compared to standard gradient descent. But again, something to keep in mind here is that the choice of learning rate does matter quite a bit, right? So here, again, the optimum is at minus 0.5, which is the center of the, minus 0.5 minus 7.5 is the center of the ellipse here. But the yellow line, which is the trajectory of momentum, has already overshot it, right? So we still have to make sure that we adjust the learning rates suitably in momentum. So we can always just adjust it down, but that again has the effect that we make lesser progress. Okay. So as you can see, there is oscillations even in momentum. So how do we make sure that so we have to reduce the oscillations, but at the same time we have to choose a reasonable step size that we keep making progress towards the optimum. So that is solved by a method called ADAM. It's called adaptive scheduling with momentum, which basically has the effect of adaptively choosing the learning rate according to what happened previously using second order information. Right, so that's the trick. So let's see how that works. Again, we'll take the same example of the ellipse. Right, so we'll take the same example of the ellipse, but add a third curve. The third curve is basically ADAM gradient descent. Okay, so ADAM takes into account the first order history just as momentum, but also scales the learning rate according to second order history, right? So there are 2 parameters, there's actually 3 parameters in ADAM. And it turns out that these parameters are it's not as sensitive to these parameters as before. So choosing these is not that difficult. You can actually just set them globally as 0.9 or 0.99. That should work. Okay, so let's see how that works on the ellipse. Right, and I'm going to take fairly aggressive learning rate here. 0.9 is a bit small. Let's choose a slightly more aggressive learning rate. So say 1.5, 1.4 is good. Okay, so here what happens is gradient descent oscillates, right? Momentum sort of smooths out the gradient descent oscillations. But Adam is doing something somewhat strange things here. Let's run it a few more steps and see what happens. Run it a few more steps. As you can see, it's beginning to point towards the right direction. And if we increase it a little more, right? So gradient descent has continued to oscillate. Momentum has smoothed it out, but sort of overshot it a bit. Because of the momentum term, we have damped it a little bit too much, perhaps, right? But Adam has tempered that effect and is now, stably going towards the optimum. So if you run it all the way to say 20, you should be able to see what's going on. So yeah, now now at this point, all the methods are almost there, but Adam has provided the smoothest trajectory and least number of oscillations, and also achieved the optimum the fastest. Yeah. So hopefully this gives you a visualization of how the different optimizers function. Typically, in deep learning, one uses one of these three methods, right? So it's either gradient descent or either gradient descent or a gradient descent with momentum or Adam. I should be a bit more clear that in deep learning we use stochastic versions of these methods, right? So we don't really look at full gradient, but a mini batch. But I didn't talk about mini batching in this exercise. It's mainly about history terms as well as learning rate. The $1 million question is, which optimizer do you use or should you use? Well, unfortunately, there's no universal answer here. It's a good thumb rule to try all of them for your particular application or your particular data set. Out of experience, a good heuristic is to use if your application involves natural language processing, such as text processing, where the data is very sparse, right? So the input features are very sparse. Then Adam seems to work really well, right? So if you're trying to train a transformer architecture for some question answering application, Adam seems to be working very well. If instead you're doing something involving images, like image classification, object detection, image generation, and so on, SGD with momentum seems to be working best. So in practice, it's always a good idea to try out all these three optimizers and see what works best.